In this video, we're going to be doing a walkthrough of the 2023 released AP Physics 1 FRQs questions. So, starting off, this is the formula sheet that you would have been given, and you would have access to this, both sides. And, okay, let's start off with question 1. So, directions. Yes, these are your 1, 4, and 5. These are going to be short FRQ problems that require 13 minutes each to answer and are worth 7 points each. Questions 2 and 3 are long FRQ questions that require 25 minutes each to answer and are worth 25 points each. Share work for each part and in the space provided after that part. Okay, so what we can see here is we have like a spring, right, attached to a wall and a cart that's being pulled by hand. And on the right, we have a kinetic energy in joules versus potential energy in joules. Okay, and what is the question? A cart on a horizontal surface is attached to a string. The other end of the spring is attached to a wall. The cart is initially at rest, as shown in Figure 1. When the cart is released, the system consisting of the cart and the spring oscillates between the positions positive x and negative l. Figure 2 shows the kinetic energy of the spring cart system as a function of the system's potential energy. Frictional forces are negligible. On the graph of the kinetic energy K versus potential energy U, shown in Figure 2, the values for the x-intercept and the y-intercept are the same. Briefly explain why this is true using physics principles. Well, okay, so we know that the x-intercepts correspond, it's a little bigger, correspond to points where the kinetic energy is equal to 0, which occurs when the cart is momentarily at rest at the turning points. Which are x is equal to plus or minus L. So those turning points are right here, right? And at that point, which we have marked on our graph here, all mechanical energy is equal to just potential energy. So U equals E total. And it's also asking about the y-intercept. So we can write an explanation for the y-intercept. So the y-intercept corresponds to the point where the potential energy is equal to 0, or College Board represents as U is equal to 0, which occurs at the equilibrium position, x is equal to 0. Now at that point, all mechanical energy is equal to kinetic energy, so you can write that K is, at that point, is equal to E total. So now, okay, so this was at the equilibrium position, x is equal to 0. See here, and then here, that. Now, what we can say is that because mechanical energy is conserved, the total energy of the system is the same at all times. Therefore, Ke max must equal to the maximum potential energy, making the x int equal to the y int, making the x-intercepts equal to the y-intercepts. So this uses the principle of the conservation of mechanical energy, and we use the physical concepts of intercepts. So this is also a clear way you should be formatting your FRQ responses. So now let's move on to the next portion. So when the cart is at positive L, and is momentarily at rest, right, the ball is dropped onto the cart. So then the block sticks to the cart, and then the block cart system continues to oscillate between negative L and positive L. The masses of the block are m initial and 3m initial, respectively. So the frequency of the oscillation before the block is dropped onto the cart is F1. The frequency of the oscillation after the block is dropped onto the cart is F2. Calculate the numerical value of the ratio F2 over F1. So now we know that before the block, the cart mass is going to be equal to m initial. And then we know that after the block, we know that the cart plus the block mass is going to be equal to m initial plus 3m initial from the block. So, and we also know that the spring constant remains unchanged. Now, what we can do for this problem is we can use familiar with the oscillation frequency formula, and that is F is equal to 1 over 2 pi over the root of K over M, right? Now, using this is for our mass spring system. Now we can write the formula for each case. So before block and after block. So before the block, we have F1 is equal to 1 over 2 pi over the root of K over M initial. And then we have after the block, F2 is equal to 1 over 2 pi times the root of K over 4M initial. And then we want to take the ratio of this F2 over F1. That is equal to the root of, we can combine the root because they're both there. And then we know that cancels out. So then we know that it's going to be K over 4M initial divided by K over M initial. That's going to equal to 1 over 4 because we can see everything else cancels out. And then we want to, and because it's on a fraction, you have to flip it, right? So that means you would just flip the whole thing to get it to the top. So then you have this is equal to 1/2. Okay, the dashed line in figure 4 shows the kinetic energy K versus potential energy U of a block cart spring system after the block is dropped onto the cart. The graph is identical to the graph shown in figure 2 for the cart spring system before the block is dropped onto the cart. Briefly explain why the two graphs must be the same using physics principles. So what can we analyze from this? Well, we know that after the block is dropped and sticks to the cart, we know that the total mechanical energy will remain constant, right? Because there is no external net forces, right? So we can write this. Okay, so after the block is dropped and sticks to the cart, the total mechanical energy of the block, cart, spring system remains constant because there is no external work done on the system. And that's because friction is negligible. Friction is negligible. Okay. And we also know that, okay, although the oscillating system increases, the cart and block continue to oscillate between the same positions. X is equal to plus or minus L, as we've seen earlier. And then because we know that, since the spring constant and amplitude are unchanged, that means that the max spring potential energy, max, is equal to 1/2 KL squared. And that is the same before and after the block is added. And okay, we have to write a little bit more, but I'll just put this up here. So, because the total mechanical energy is conserved and equals to the max, or is equal to U max, we'll just say U spring max, that means the relationship between kinetic energy and potential energy remains unchanged. So that's why, therefore, we can say K versus U graph is identical. After the block is dropped onto the cart, consider a system that consists only of the cart and the spring. On figure 4, sketch a solid line that shows the kinetic energy of the spring that consists of the cart and the spring, but not the block after the block is dropped onto the cart. Okay, so what we know is that post the block drop of which is the dashed line. Well, for the dashed line is just kinetic energy versus potential energy. For the block plus cart plus spring system, for this system, right? And in this system, we can when we write up all the energy, that's gonna be K total plus U is equal to the E total, and that's gonna be constant. And if we just solve for K total, for K, that's just gonna be the total energy minus U. So that means that was why this was a straight line and it has a negative slope. Now for the cart spring system only, and we also know that this dashed line is the same before and after the block was dropped. She answered up there. Okay, but for the solid line only, like, we had a system change, right? Because we took the block out of the system. the block is no longer part of the system. It's just the cart spring system. So that means that now this changes everything, right? So now we have to like rewrite the equation for the total kinetic energy, right? So K total. Okay. The K total was actually this, right? So K total was this. That means if your K cart is just rearranging that. And then now the block is outside of the system. So now we had to exclude the kinetic energy from the block, right? So then at any spring potential U, like any U, that means some kinetic energy, like some of the kinetic energy, it belongs to the block, right? So that means the cart alone, and then we just have like the cart alone, right? So that means it has less total kinetic energy. So what that means is that like, that means the slope is still the same, right? Because it's still kinetic energy equals E minus U. So then it's still same, m is equal to -1, right? And then you still have the same x int because you still have the same max, you still have the same US max, right? But we know that what changes is we're gonna have a lower y-intercept because we're removing some of the kinetic energy, right? Because US is just this. And we're just gonna lower the y-intercept, I'll say. Lower the y-int because we removed the kinetic energy. So changing the system changes the y-intercept, not the x-intercept, as long as the spring reaches the same max compression. So, yeah. So because the dashed line is the block cart spring system, and that's one closed system, right? A closed system, right? With conserved mechanical energy, right? So that's for the dashed line. But then, for the dashed line. But then for the solid line, it has to lie like slightly below it. So that would be like this, right? Because some of the kinetic energy, it was the blocks. And then, so that means the cart spring system, it has less kinetic energy at any given potential energy. So here, the y-intercept is when your potential energy is equal to 0. And that's when that occurs when your kinetic energy is at its system max. And that means you have no spring compression. And then all the system energy is just kinetic energy. And that's dependent on how much kinetic energy the system has. While the x-intercept is when your kinetic energy is equal to 0, and then your potential energy of the system is at its maximum. And that's when you have that's when you have max spring compression. And that means all your system energy is energy is actually potential, and that's dependent on the max amount of potential energy that your system has. So now we can move on to our next question. So we're on to 2. So students conduct an experiment to determine the acceleration A of a cart. The cart is released from rest at the top of the ramp at time t equals 0 and moves down the ramp. The x-axis is defined to be parallel to the ramp with its origin at the top as shown in the figure. The students collect the data shown in the following table. So what we have is, so the cart, it rolls down the ramp from rest. So it starts at rest. And then we have this data table here. Okay, and now indicate what quantities could be graphed to yield a straight line whose slope could be used to determine the acceleration A of the cart. You may use the remaining columns in the table as needed to record the quantities that are not already in the table. So what are we doing? We want a straight line. So that means we're linearizing the data. So what we want to choose quantities. We want to choose quantities that produce a straight line, and we want the slope to equal to acceleration. And remember, acceleration, delta V over delta T. And we know that up here we wrote like, the cart starts at rest, right? So that means we can use x is equal to 1/2 at squared. And this is going to be linear. This will be linear if we plot as our y-axis, we make it x, our displacement, and we make our x-axis into t squared. So what we're trying to do is we're just trying to like, so this would be our y equals mx plus b. We make that our y-axis x, and then we make our x t squared. Okay, t squared, that's going to be our x right there. Now, we can write this here. So our vertical axis would be x in meters, and our y-axis would be t squared in seconds. Now, what we have to do, we want to plot the graph. So, on the following grid, plot the appropriate quantities to create a graph that can be used to determine the acceleration A of the car as it rolls on the ramp. Clearly scale and label all axes using units as appropriate. Draw a straight line that best represents the data. Okay, so what we had to do is we have to get x and we have to get t squared. But thankfully for us, we already have x. So now we just need to get t squared, which we can calculate in this table. So you're just going to square each of these, right? So 0.39 squared, that's, if you'll have your calculator for this, so that'll be 0.152. This is going to be, well, I'll just write squared for all these. So 0.59, that's going to be 0.348. This is going to be 0.593, and this is going to be 0.922, and this is 1.44. So now we can take these points. I'll write them over here for us. X, Y, so we have, or I'll just write as an ordered pair. So we have 0.152, 0.06, we have 0.348, 0.14, 0.593, 0.24, and we have 0.922, 0.37, 1.44, 0.55. So, okay, now label our axes. We have, vertically we have x, and that's in meters. This is t squared in seconds. Now, okay, we can graph this. So this is what we did for this point. This is just one of the ways you can linearize that equation. And remember, linearization just means you just convert it into a form that's like y equals mx plus b. And you just wanna like generalize stuff like this. Just because this is t squared, don't let this throw you off, because we can just like, t squared is just like the values, how you get these x values. Like, it doesn't matter if it was squared or not, so don't let that deter you. It's still linearized. So now, use the line you just drew in part A to calculate an experimental value for the acceleration A of the cart as it rolls down the ramp. So we can use the slope. So we can use x is equal to 1/2 at squared to get the slope. So from this, we can identify our slope is equal to 1/2 a. 1/2 a, because that was, t squared was our x, right? T squared was our x, and x displacement was our y, right? So from here, after this, we can see that a is equal to 2, which is our slope, times slope. Now, we can estimate the slope from a best fit line. So we can say that slope is equal to, let's just choose 2 of our points. So we can do we can do our last point. Why not just do our last point, and we can do our 0.56. We can do our first point. So now doing this, we have 0.55 minus 0.06. I divided 1.44 minus 0.152. If you type that into your calculator, you have 0.49 over 1.288. That's approximately 0.338 meters per second squared. We have 0.152, and then we have this. So now we have to calculate the acceleration. So acceleration is equal to 2 times 0.38. And that's equal to 0.76 m over second squared. That's from taking this 0.38. This was the slope. The students are asked to determine experimental value for the acceleration due to gravity g experimental using their data. What additional quantities do the students need to measure in order to calculate g experimental from A? Well, if we want to relate the acceleration on the graph to gravity, let's see here. What we can see is, okay, so we have F is equal to MA, summation of F is equal to MA. And then we have mg sine theta from inclined planes is equal to MA. So what we need is, okay, so we need the students must measure the angle of the ramp. Now, to write g experimental in terms of A, well, what we can do is we have summation of forces is equal to MA. So then we can write mg experimental sine theta that we got up there is equal to MA. We see the m's cancel out. So then we see g experimental dividing both sides by sine. We have A over sine theta. The students calculate the value of g experimental to be significantly lower than the accepted value of 9.8 meters per second squared. So, what is a physical reason other than friction or air resistance that could lead to significant difference in the experimentally determined value of g experimental? Well, an example could be that, that the ramp angle measured was too large. It was an overestimate. Wrong. So it was wrong. So I'll briefly explain how the physical reason you identified in part C would lead to, C1 leads to a decrease in the experimentally determined value of g experimental. Well, we know that if theta was overestimated, that means sine theta would be too large, and then when you divide, well, we have g experimental as this expression, right? So if this is the case, then we would divide. So then dividing by a large number makes g experimental smaller. So it would go down. The students want to confirm the acceleration is the same whether the cart rolls up or down the ramp. The students start the cart at the bottom and give the cart a quick push that it rolls up the ramp and momentarily comes to rest. The x-axis is defined to be parallel to the ramp with the origin at the top. On the following graph, sketch the position x and velocity v as functions of time that correspond to the scenario shown while the cart moves up the ramp. So, when the cart moves up the ramp, initially we have that like the x is going to be large, and then it goes down, and then after that it rolls back down the ramp, right? So that's why we can see that for the position time graph. And then after this, we can see for the velocity time, initially it's negative velocity, then the velocity will be 0 for a moment, and then it will go up. So that explains that. Now for this, a small block of mass m initial is attached to the end of a spring of constant k initial that is attached to a rod on a horizontal table. The rod is attached to a motor so that the rod can rotate at various speeds about its axis. When the rod is not rotating, the block is at rest and the spring is at its unstretched length L, as shown. All frictional forces are negligible. Okay. At time t is equal to t initial, the rod is spinning such that the blocks move in a circular path with a constant tangential speed v initial, and the spring is stretched to a distance d initial from d1 from the spring's unstretched length, as shown in figure 1. At time is equal to t2. The rod is spinning such that the block moves in a circular path with a constant tangential speed v2, and the spring is stretched a distance d2 from the spring's unstretched length, where d2 is greater than d1, as shown in the figure. Okay, so what we're being asked is we want to identify and compare the forces that are acting on the object, and then we want to justify it, and we can use Newton's laws. So first we can see, let's identify all the forces. So for an object moving on a surface or interacting with another object, the forces that we usually have the weight, which is mg, and the normal force Fn perpendicular to the surface, and applied or interaction forces, and possible friction. Let's see here. But frictional forces are negligible, so no friction. So now we want to draw the FBD for this. On the following dots, which represent the block at the location shown in figure 1 and figure 2, draw the force that is exerted on the block by the spring at times t is equal to t1 and t is equal to t2. The spring force must be represented by a distinct arrow starting on and pointing away from the dot. Draw the relative lengths of the vectors to reflect the relative magnitudes of the forces exerted by the spring at both times. Okay, so what we had was a block of mass m initial that was attached to a spring, which is spring constant k initial, and the spring is attached to a rod rotating on a horizontal table, right? We have no friction, and then when it's rotating, we know that it's going to be moving in uniform circular motion, and it stretches a distance d, and we know the radius of the circle radius is going to equal to L plus d. So something we need to know is that the spring force is going to equal to the centripetal force. So now going back to our force diagrams, at both times t1 and t2, we have one vector, and they're both going to be radially inward. So that's toward the rod, and then that's going to be to the right because we have our masses. They're both over here. They're both going to be going in to the rod. That is going to be inwards to the right for both of them. Now, let's think. So we know that at T2, this distance is D2L. So we know that the spring stretch is going to be greater because we know that D2 is greater than D1. So that means that the F spring 2 is going to be greater than the F spring 1. So both the arrows are going to be pointing right, but we know that T2 is going to be longer, so we can draw that. Referencing D1 and D2, describe your reasoning for drawing the arrows a length that you did in part A. So we know that the spring is stretched farther at time T2 than time T1. And since the spring force increases with stretch distance, the spring exerts a greater force on the block at T2. Therefore, T2 is longer. That force is longer. Again, D2 is greater than D1, and we also know that force depends on stretch. Now, comparing the speeds, we know that V1 is going to be less than V2. And the reason is because the net force on the block is going to be the spring force. And we know that a greater spring force produces a greater centripetal force. And a greater centripetal force corresponds to a greater tangential speed. And since the spring is stretched more at T2, that means that the block must be moving faster. So we know that, again, that the spring force is the net force. And the net force relates to speed. Okay. Consider a scenario where the block travels in a circular path where the spring is stretched a distance d from its unstretched length L. Determine an expression for the magnitude of the net force F net exerted on the block. So, what can we do for this? We can write that. Okay. So, let's see here. We know that we know that F net is equal to K initial times D, right? So that's spring constant K. Constant K. And there is no centripetal force yet. Now, to derive, derive an equation for the tangential speed V of the block. Express your answer in terms of M initial, K initial, L, D, and fundamental constants as a... So we can do this by starting off with Newton's second law. And from Newton's second law, we can identify the forces and acceleration. So we know that the net force from above is equal to the spring force. And because we know that, we can write that F net above we had is equal to K initial times D. And because we know that acceleration is centripetal, we can write that AC is equal to V squared over R. And we know that the radius is equal to the length plus D. So now we can substitute this into Newton's second law. So if we know that Newton's second law is equal to the net forces, we can rewrite that entire expression to be K initial times D is equal to M initial times V squared over L plus D. Because here we can see that radius is here, and we just keep the V squared. And from here, we can write that, from here we also move the, we have, that's your acceleration. And then our M was just that. F net, that was just that. Now, if you rearrange to solve for v squared, you have v squared is equal to k initial times d times L plus d, and you can divide all of that by m initial. And then you can take the root of both sides, and then you just have that v is equal to the root of k initial times d times L plus d divided by m initial. Does your equation for tangential speed v of the block from part B2 agree with your reasoning from part A? Yes, it does. And that's because from part B, we have our tangential speed is v is equal to the root of k initial times d times L plus d divided by m initial. And what this equation shows is that as the stretch d increases, the tangential speed v also increases. We can see that they're directly related. V and d they're proportionally, so this agrees with the reasoning in part A, where in part A we wrote that, well, we know that a spring stretch or a greater spring stretch resulted in a greater spring force and therefore a greater speed. A block of unknown mass is stretched to a long, lightweight string that is wrapped several times around a pulley mounted on a horizontal axis through its center, as shown. The pulley is a uniform solid disk, mass m, and radius r. The rotational inertia of the pulley is described by the equation I is equal to 1/2 mr squared. The pulley can rotate about its center with negligible friction. So that means you have no net external forces. Therefore, we have conservation of momentum. And also the string does not slip on the pulley as the block falls. When the block is released from rest and as the block travels toward the ground, the magnitude of the tension exerted on the block by the string is Ft. Determine an expression for the magnitude of the angular acceleration of the disk as the block travels downward. Express your answer in terms of m, r, Ft, and physical constants as appropriate. Okay, so what we can do is we can start with the rotational version of Newton's second law, and that's going to be the sum of the torque is equal to the inertia, the moment of inertia, times the angular acceleration. Now, what we have to do is we need to identify the torque. So the torque, we can see that the tension force Ft acts tangentially at a radius r. We can see that here, Ft. So now from that, we can see that the torque magnitude is equal to the force of the tension times the radius. See, the radius is here, and the radius here. That's because, we can see that if this is, we can see here, if we just draw, that's the line, then we see the radius here. We can see that this is 90 degrees, so that is tangential. So that is the formula for the torque, knowing that torque is equal to F sine theta. And from here, we can substitute in the rotational inertia. So if we know that FTR is equal to 1/2 mr squared times the times alpha, right? That was our moment of inertia up here. And we're just going to move that down. So, and then torque T is equal to this whole expression, this expression right here. So now we can solve for the angular acceleration. That's just going to be equal to 2 over ft divided by m over r. And now you can rewrite that at is equal to 2ft over mr. And then you would box this. Scenarios 1 and 2 show different pulleys. In scenario 1, the pulley is the same solid disk referenced in part A, so same moment of inertia, and same other things that we just solved for. So in scenario 2, the pulley is a hoop that has the same mass m and radius r at the disk. Each pulley has a lightweight string wrapped around it several turns and is mounted on a horizontal axle as shown. Each pulley is free to rotate about its center with negligible friction. In both scenarios, the pulleys begin at rest. Then both strings are pulled with the same constant force Fa for the same time interval delta t, causing the pulleys to rotate without the string slipping. After the time interval delta t, the change in angular momentum of the disk is equal to the change in angular momentum of the hoop, but the change in rotational energy for the disk is going to be greater than that of the hoop. So, consider scenarios 1 and 2 at the end of the time interval delta t. In a clear, coherent paragraph length response that may also contain equations and drawings, explain why the change in angular momentum of both pulleys is the same, but the change in rotational kinetic energy is greater for the disk. So, even though the change in angular momentum for both of the pulleys is the same, the change in the rotational kinetic energy is greater for the disk. So, what this means is that for the torque, we know that torque is the same. That's because both pulleys experience the same Fa that is applied at the same radius r. So that means that our formula for torque was Fa times r. So that means they have the same torque and have the same torque. We also know that you have the same angular impulse, which means that you will have the same change in angular momentum. So we know that the formula for angular impulse is delta L is equal to tau torque times delta T, change in time. And we know that both pulleys have the same torque and same time interval for which that they are measured. So the change in angular momentum is the same for both pulleys. Now, on the other hand, we know that the rotational inertia is different for both. And the rotational inertia formulas you should generally memorize since they did not give it to us here. So we were given inertia of the disk earlier, which is 1/2 r squared. And you should know that the inertia of the hoop is just mr squared. So we know that the hoop has the greater rotational inertia, and that's because more mass is farther from the axis, while the disk has more mass that's closer to the axis in total. And we know that different inertia will result in different angular kinematics. And we know again that angular momentum is represented by L is equal to the moment of inertia times the angular velocity. And because we know that the change in angular momentum is the same, and we also know that the inertia of the hoop is greater than the inertia of the disk, then we know that the disk must have a larger angular speed change than the hoop. Now, but now we have to discuss, why does the disk gain more rotational energy? Well, that's because the rotational kinetic energy, rotational, is equal to 1/2 of the moment of inertia times omega squared. Let's say because the disk has a smaller rotational inertia, but it has a much larger angular speed, because omega squared matters more than moment of inertia I. That means that the disk gains more rotational kinetic energy than the hoop. So overall, we can see that what we see from our explanation is that the torque applied to each pulley is the same because the same force is applied at the same radius. So these radiuses is the same. So therefore the torque tau is the same. So hoop, disk, also hoop, R disk. And because the pulleys experience the same torque for the same amount, for the same time interval, for the same amount of time, that means we saw that the angular impulse, was the same, and that means that the angular change in momentum is also going to be the same. But we know that the rotational inertia of the hoop is greater than the the rotational inertia of the hoop is greater than the rotational inertia of the disc, because more of its mass is distributed farther from the axis of rotation. And then since we know that the angular momentum is equal to the rotational inertia times the angular velocity, that means that the disk must have a greater angular speed than the hoop. And because the rotational inertia depends on the square of the angular speed, that means that the increase in the rotational kinetic energy for the disk is greater than the hoop. A rod with a sphere attached to the end is connected to a horizontal mounted axle and carefully balanced so that it rests in a position vertically upward from the axle. The center of mass of the rod sphere system is indicated with an X as shown in figure 1. The sphere is lightly tapped and the rod sphere system rotates clockwise with a negligible friction about the axle due to gravitational force. A student takes video of a rod rotating from the vertically upward position to the vertically downward position. Figure 2 shows 5 frames, still shots, that the student selected from the video. Note that these frames are not equally spaced apart in time. Okay, so we have this rod sphere system that's rotating around the horizontal axle, and the system, it starts vertically upward. It rotates clockwise under the influence of Fg, and we have the friction is negligible. So, and we also know that the center of mass, well, from here we can conclude that the center of mass of the rod, okay, so your system is going to be 3/4L from this. Okay, 3/4L. And we have the first 5 video frames that show the motion due to this vertically downward position. So let's start off with A. Use the frames of the video shown in figure 2 to answer the following questions. In which frame is the angular acceleration of the rod sphere system the greatest? And justify your answer. So we know that using angular acceleration related to torque, we know the angular acceleration is going to be proportional to t. That's proportional. The symbols look very similar, so I just want to make that clear. And we know that torque from gravity, the torque is going to equal to r times F sine of theta. So we want to find where is the torque where is the angular acceleration the greatest. So when we look at the force of Fg, it's always acting down, right? So when is it going to be the greatest? Okay, G here, and here. So the arm is pointing this way, right? Like, focus on the arm. It's pointing this way. And how do we know when the torque is the greatest? Well, the torque is greatest when it's at 90 degrees. And that's because sine of 90 degrees is equal to 1. So it'll be greatest when it's 1, and that's frame C. So frame C, because sine of 90 degrees is equal to 1, which will maximize our answer. So we know that in frame C, the rod is horizontal, and Fg, the force of gravity, acts vertically downward. So therefore, the force is perpendicular to the radius. And this makes the lever arm maximum. Arm maximum. And hence, the torque is greatest. And since we know that angular acceleration, again, up above of us, was proportional to torque, that means that angular acceleration is also greatest. Now, the rod sphere system has mass m and length L, and the center of mass is located a figure 3/4 L from the axle as shown in figure 3. Derive an expression for the change in kinetic energy of the rod sphere system from the moment shown in frame A. Oh, I just realized I wrote this. We forgot to answer part 2. So for part 2, where is the rotational kinetic energy the greatest? Well, we know that the system starts from rest, and also we know that, so we know the system starts from rest, right, up here. And we know that gravity, it applies torque in the same direction the entire time, because gravity is always down. And then we know this system, it continuously speeds up. And we know that rotational kinetic energy is equal to KR, is equal to 1/2 moment of inertia squared. So we know that a moment of inertia squared, we know that the angular velocity is the most important and takes the largest precedence when we're calculating that rotational kinetic energy. So we want to find when is omega the greatest. So looking at all of these, our angular speed is going to be the greatest omega. This was the greatest torque because of that perpendicular. Earlier we had this. This has the greatest omega. And this is because, so we know that because the system starts from rest and FG applies torque in the same direction the entire time, and we know the system continuously speeds up from rotational kinetic energy, KR is equal to 1/2 omega squared. We know angular speed omega is greatest at frame E. Frame C and frame E. So for this question, this response was for this question. Derive an expression for the change in kinetic energy of the rod sphere system from the moment shown in frame A to the moment shown in frame E. Express your answers in terms of ML and the fundamental. So we want to find the find this. So we can start off with the conservation of energy, because there's no net external forces, right? So we can use conservation of energy. Use conserve of energy. So we have E initial is equal to EF. Therefore, we can write that UG initial plus K initial is equal to UG final plus K final. Now, we can apply our initial and final conditions. So we know that from rest, K initial is equal to 0 because we start from rest. So we have that, no movement. And we also know that delta K, we have delta K is equal to KF minus K initial, 0, which is equal to KF. Now we want to find the change in height. Okay, so change in height, right? So we know from the diagram, change in height. So from the diagram, we know that the center of mass drops from above the axle to below the axle. So it goes from here to there. So we know that center of mass drops from above to below the axle. So that means that if we were to write the total vertical drop, delta Y, total vertical drop, that's going to equal to 3/2 times L. Now, what we want to do is we want to convert gravitational potential energy into kinetic energy. And in order to do that, let's move this up a little bit. In order to convert the gravitational potential energy into kinetic, we have delta K is equal to mg delta Y. Now, delta K, if we substitute in what we just got here, we have 3/2L. So this entire expression is going to equal to 3/2 mgL. And we can actually put this over here. Briefly explain why the rod and sphere gain kinetic energy even if Earth is not included in the system. And this is a lot of writing. The rod and sphere gain kinetic energy because FG does work on them when Earth is not included in the system. FG is an external force, and external forces can do work that changes the kinetic energy of the system. So in total, you should have completed, this is question 5.